Right. Thanks for the introduction. Welcome to my talk. My name is Matthias Poloczek. I'm presenting joint work with Georg Schnittke, my former advisor from Frankfurt, my host at Cornell, David Williamson, and Anke van Zulen from College William of Mary. So the title of the talk is New Approximation Algorithm for MACSET. I'm going to show two new algorithms to you, which are simple and fast. I think we'll agree on that. And I will provide some evidence that they are excellent in practice, and we'll see if I can convince Bill about that. So let me start with an introduction to MACSET. In the maximum satisfiability problem, we are given a set of clauses with non-negative weights, and want to find an assignment to the variables which satisfies clauses of a maximum total weight. So in this example, we're given three clauses, x or not y, not x or y, and the unit clause, the clause of length 1, not y. If I would fix x to 1 and y to 0, I would satisfy the first clause, but the second clause would be unsatisfied because both literals evaluate to 0. And the third clause, unit clause not y, would also be satisfied. On the other hand, I could do better. If I fix both variables to 0, I have a satisfying assignment, meaning that I satisfy all clauses. Well, if I satisfy all clauses, I know this is optimal, right? I can't do better than that. Why study MACSET? MACSET is mostly known in the theory community because of its role in the PCP theorem, in the hardness of approximation. But besides that, there are natural applications where we can reduce problems to MACSET, particularly whenever we optimize in the presence of contradictory objectives. We might try to reduce the problem at hand to MACSET. So examples are, for instance, resource conflicts. I want to plan something, schedule. This might be a natural representation. But also in bioinformatics, they recently reduced problems to MACSET. So in an ideal world, they would have a Z instance, because in a perfect world, the data would have no noise, and then there would be a natural explanation that explains all the data we've found. But in practice, things are a little different. They have a lot of data which is inconsistent, and therefore they cannot hope to find an explanation for all the data, explanation corresponding to an assignment of variables that satisfies all clauses. But maybe also another point to make, there is a conviction that the progress in MACSET solvers actually fuels the applications of MACSET. So they say up to a couple of years ago, MACSET solvers were very good. We could not solve these instances of large sizes, but now MACSET solvers become better and better, and therefore the number of applications increases dramatically. Let me briefly discuss the previous work. MACSET is known to be APX hard, so we settled for the approximation. The typical quality measure of approximation algorithm is the so-called approximation ratio, meaning that we divide the score of the algorithm, which is just the weight of clauses satisfied by the algorithm, by the score of the optimal solution. And this is evaluated for a worst case input, so it's a worst case guarantee. And Hausdorff has shown in 2001 in a seminal paper that we cannot hope to be better than 7/8 approximation unless P equals NP. On the other hand, a variety of techniques have been applied to MACSET. The first algorithm is due to Johnson, 1974. It's a deterministic greedy algorithm, and he showed a guarantee of 1/2. This was improved later by Chen, Friesen, and Zheng to 2/3, and 2/3 is tight for this algorithm. Yannakakis proposed a 3/4 approximation algorithm based on linear programming and flows. And the same approximation guarantee was obtained by Goemans and Williamson by a much simpler algorithm that just solves an LP and afterwards rounds the solution. The currently best known algorithm is due to Abidor, Bagwich, and Zwick. It's an SDP-based algorithm, so we run several simple programming-based algorithms in parallel and output the best solution. And they prove that this best solution is almost a 4/5 approximation. In particular, we still have a gap between the best hardness bound due to Hausdorff and the best guarantee we have. Questions? In fact, the bound that we know for max3 set is the hardest bound that we know. So for max2 set, it's 0.95. And if the clauses get longer, the approximation becomes easier. This, in fact, for 3 set is the hardest lower bound, or the highest lower bound, whatever, that we know of. And this is actually tight. So if you know that the input has only clauses of length 1, 2, or 3, we can get a certain weight approximation by an SDP-based algorithm due to sorry? Oh yeah, right. This is for arbitrary clause length. So yeah, particularly when you're proving lower bounds, we use clause of length exactly 3, but from an algorithm we expect that it can deal with all clauses, all clause lengths. Sorry? This is only max 3 set, right? I mean, yeah, there's this notion of approximation resistance. So if you have clause of length exactly 3, a random assignment gives you 7 weight approximation. So the problem is to deal also with shorter clauses. Okay, let me also give you a brief history. So Schnittger and myself at Soda 11 gave the first 3/4 approximation algorithm that does not solve an LP. In particular, we consider the variables in arbitrary ordering. And then for each variable, look at the clauses it appears in, particularly look at the clauses that are not yet satisfied. Then we make a random decision for this variable. And then forget about it, look at the next. So we work in an online setting, it's very local, and we can show approximation ratio 3/4. And the analysis is based on a local invariant that relates the satisfied weight and expectation to the loss and the optimum. And I will come back to that later. But this is the overall framework that was also subsequently used in the upcoming papers, the later papers. So at ESA, I gave an improved performance guarantee where I relate the weight of the satisfied clauses to the objective value of the canonical LP relaxation rather than the integral optimum. And this gives a better bound because the LP is at least as good as the integral, of course, but it can be higher by a factor of 4 with 3. Van Zulen proposed an elegant set of assignment probabilities. Bookbinder, Feldman, Nauer, and Schwartz at Fox gave a 3/4 approximation algorithm as part of their work on unconstraints of modular maximization. So they have this greedy algorithm for unconstraints of modular maximization. It gives them 1/2 approximation. And this algorithm can be turned into a 3/4 approximation for maxset. And then in Latin, Williamson, Van Zulen, and myself showed that in fact the BFNS algorithm and Van Zulen's algorithm are the same. And moreover, we gave a simple proof based on the BFNS framework. So we can get 3/4 without solving LP, but still this is a randomized algorithm. So the challenge we face in the first part of the talk is, can we also get the same result deterministically? And there's some problem to overcome. The first question is, when can we just randomize the algorithm? And in order to prove that this is hard, we consider adaptive priority algorithms. This is an information theoretic model proposed by Brody, Niels, and Rackroff, 2003. And the idea is to capture, to formalize the behavior of deterministic greedy algorithms. Particularly, we think again that the algorithm explores the input piecewise, so variables and a set of clauses, and makes an irrevocable decision for each part before going on to the next part. This is the overall model. And what it distinguishes from the online model is that the adaptive priority algorithm has the ability to choose the variable ordering. This is the third point is what makes it non-trivial. And there's some evidence that the variable ordering is an influential parameter. So on the one hand, we take John's deterministic greedy algorithm and use a randomized ordering, a random permutation, rather than an arbitrary ordering. This improves the worst case guarantee by a small constant. It was shown by Costello, Shapiro, and Titterly at Soda 11. Moreover, if we only have a 2-CNF, if we have clauses of length 1 and 2 only, then Schnittger and myself showed that we can always find that there always is an ordering. We cannot find efficiently, but there is an ordering such that Johnson's algorithm gives an optimal solution. Yeah, in ESA 11 I showed that no such deterministic greedy algorithm can actually achieve a 3/4 approximation. Particularly, they cannot beat 0.729 for a certain representation of the input, which is strong enough to run our algorithms, but also allows us to prove information theoretic bounds. So we have to overcome somehow this approximability bound. And here's what we do. So last year I gave a talk about it at Banff, and then afterwards Ola Svensson said, why don't you just randomize probabilities in the second pass? And that's what we do. We call it a two-pass algorithm for MaxSat. Idea is as follows. We consider in both passes the variables according to some arbitrary ordering. In the first pass, we just compute assignment probabilities. We compute a probability which we set the variable to 1, but we don't do it. We defer decision to the second pass. So if we can show that we can compute an assignment probability for each variable, that if we fix each variable independently according to its respective probability, this would give us a force approximation expectation. Then the second step, the second pass, we can just use the method of conditional expectation to de-randomize this random assignment. And therefore, the second step is trivial. We focus on the talk on the first step, on the first pass. Let me motivate how we should choose the assignment probabilities in the first pass. So as that we use an arbitrary, yep. So we're proving now that this two-pass algorithm has an approximation ratio of 3/4 by showing that we can find assignment probabilities in the first pass, such that if we would set each variable according to its assignment probability, we would get a 3/4 approximation in expectation. And then we can easily de-randomize this assignment by using. Okay. Further questions? Okay. So I want to give you some motivation how the assignment probability should be chosen, what should be traded off in when we determine the assignment probability, when we fix a variable randomly. And there are two alternative strategies, right? On the one hand, I could try to maximize greedily in each step the satisfied weight. And if E of set I is the expected weight, if I would fix the first I variables randomly, independently, according to the probability, then I could try to maximize that, which would just mean, okay, in fact, we will set the next variable deterministically. So for this clause that, for instance, I want to fix x, I would satisfy a weight of 1 plus epsilon by fixing x to 1, would satisfy a weight of 1 by fixing x to 0. So a greedy strategy would just fix x to 0 deterministically. But this doesn't work. We only would get the first clause, but not the second one. So we'd get, in fact, a 1/2 approximation here. So being completely greedy doesn't work. The complementary strategy would be to maximize the weight of clauses that are not yet unsatisfied. This is a very cautious strategy. And W denotes the total weight. E of unset I is the expected unsatisfied weight after fixing the first I variables. That would apply a strategy that tries to maximize this quantity in each step. I would fix x to 0 in order to get the unit clause, to rescue the unit clause. But then the next step, I will have to decide whether I want to satisfy this clause or this clause. I cannot get both after I fixed x to 0. And this strategy is too cautious. But still, basically, it sets the parameters for how to determine the assignment probabilities. So we call BI our valuation of the random assignment to the first I variables. And this is just the midpoint of the expected satisfied weight, if I would fix the first I variables, and the not yet unsatisfied weight, where you try to trade these things off. And then B0 is just half of the total weight. Why is that? Well, when I start, before I fix any variable, satisfied weight and unsatisfied weight are both 0. On the other hand, after I fixed all variables randomly, each clause is either satisfied or unsatisfied. So after fixing all variables, this is just twice set I. So in particular, Bn is just the expected satisfied weight. So this gives the motivation. We want to increase Bn as far as possible, but we have to do it carefully, as we saw before. Okay, let me define the assignment probabilities. When looking at a variable, I look at the clauses the variable appears in. Then basically I look at what would happen if I would fix the variable to 1. This would be would correspond to the green increment in the B value. And I compute what would happen if I would fix it to 0. This would be the red increment. And the gist is both these values can be determined efficiently. I only have to look at the clause that the variable appears in. The whole thing is very local. and can be computed very fast. That's why we get a fast overall approximation algorithm. Then using a fact that both increments sum up to some negative value, what should I do? How should I choose my assignment probability? Well, if one of these values is non-positive, this means I make no progress when I would choose that value with a positive probability. That's why in this case I would always pick the other assignment deterministically. And if I make some progress for either choice, well, then I make a carefully biased random decision, and this decision is just biased towards the larger increment. And that's the natural thing you would do. Interesting thing is this works. I want to briefly discuss the analysis, but not go too much into the details here. So for the analysis, I fix an optimal assignment as reference. So X star is an optimal assignment. Now I want to track the progress of the algorithm, or the loss of the algorithm, with respect to this assignment. And how do I do that? Well, the algorithm computes an assignment probability for xi or for x1, and then I basically replace the optimal value by this assignment probability, by this fractional value, and so on. And then I can compute opt-i after having computed probabilities for the first I values. I let opt-i denote the expected weight I would get. I would fix the first I variables randomly according to their probabilities, and the others optimal. And again, there are two simple quantities here. Opt0, before I've made any adjustment, it's just the weight of the optimum. And after each variable has been replaced by the probability, it's just the expected weight. Particularly, the difference between two of these opt values is the expected loss if xi was fixed randomly. And now the gist of the whole analysis is this invariant. This is the key invariant which bounds the loss with respect to the optimum in each step. I think we can show that the loss in the optimum is at most the progress or the benefit in the b value. So I'm not going to show that. This is about a 3-page proof. But I'm going to show how this easily implies the overall guarantee. So let's look at this interval. On the right-hand side is the weight of all clauses. Left endpoint is 0. Then we know the midpoint is just w over 2. So where's the optimum? On the right side. The optimum. This is the fraction I would get from a random assignment. The optimum is at least as good as that. Right. Okay. Now let's run the algorithm. First step. The b value increases. Opt might decrease if we make a bad decision with positive probability, and so on. And in the end, we know that both meet in the same point, bn, which is just the weight of all clauses. Satisfied expectation by fixing all variables. Okay. Now the gist is, according to this key invariant over here, the length of the blue arcs is at least the length of the red arcs. Or put differently, the length of the blue arcs is at least half the distance between b0 and opt0. So that's what we denote here. And then basically just rewriting things, putting b on the other side, we see that the expected satisfied weight is at least half the optimal value plus a fourth of the optimum. Okay, that's it. We summarize the first part. Deterministic two-pairs algorithm satisfies clauses with at least half of the optimal weight plus a quarter of the total weight, which is at least a 3/4 approximation. And the algorithm is deterministic, simple, no flows, no linear programming. And it can be implemented in linear time. And this, again, is because of the locality of each step. And using ideas of the ESA paper, we can also get an improved guarantee of half of the LP value plus a quarter of the total value. In our paper, we also show that this analysis is tight. Okay, in the second part of the talk, I want to show you some experimental results about the deep two-pass algorithm and other algorithms. Particularly focus on fast approximation algorithms for MaxSat. And the 3 questions I want to study in this talk are: how do the algorithms perform on instances that stem from industrial applications? Second question is the randomized greedy algorithm actually better than Johnson's algorithm? So I mean, that was the whole point in sitting down and trying to prove a better approximation guarantee. And the third point is, the third question is, want to see how these algorithms compare to algorithms of other paradigms. So this talk, I will only talk about local search algorithms, but in the paper, you also find complete solvers. Complete solvers have additional ability. They can certify the optimality of the solution that does not satisfy all clauses. These are, they not only find optimal solutions, they also provide certificates. And they will also compare it in the paper to certain specialists, algorithms that perform very well on, say, random instances, fare very well on crafted instances. So these algorithms are, usually their performance peaks in one category. Okay, but here we talk about local search. What's the benchmark set? We take 1,400 instances from the SAT and the MaxSAT competitions. Those competitions are held every year, and you can submit your algorithm, and then basically they get evaluated. And the best 3 competitors get an award in each category. And for us, the most interesting category is the industrial category. And the instances, for instance, encode formal verification of processor designs, attacks on cryptographic algorithms, transportation problems, problems like that. Besides, those benchmark sets also contain crafted instances, for instance, max cut in random graphs or special graph classes, graph isomorphism problems. And a very famous category is, are the random clauses. Yeah, so those particularly contain very unsatisfiable instances where no algorithm gets more than 4/5 of all clauses. To give you some idea of the magnitude, for industrial instances, the mean is 500,000 variables in 2 million clauses, so they are rather big. But there's a huge spread. So the smallest instance has 27 variables in 48 clauses, and the largest instance has 14 million variables in 53 million clauses. And just to give you an idea how fast greedy algorithms are, so our implementation of the greedy algorithm solves this instance in less than 10 seconds. And the SAT benchmark typically contains much larger inputs than the MaxSAT benchmark, and this can be understood as that somehow SAT solvers are much more scalable currently than MaxSAT solvers. Okay, what's the measure of the evaluation? We look at the totality ratio, where we replace in the denominator the optimal value by the number of clauses in the input. And the reason is that for many inputs, we just don't know the optimal value. And then we average this ratio, the average of satisfied clauses over the clause in the input, over all instances in the respective category. And that's what we report now. Particularly, we focus on the SCAP category. This is a SAT competition. And among the SAT competition, the applied benchmarks. This is about 300 instances. And looking at how the Johnson algorithm, the greedy algorithm, and two-pass algorithm perform, we have on the horizontal axis the average time, and on the vertical axis the average fraction of satisfied clauses. We see that the Johnson's algorithm performs better than the randomized greedy algorithm, which is a slight disappointment, to be honest. And this picture we always see among all categories, so apparently this is just how it is. More interestingly, the two-pass algorithm, which is the de-randomization of the randomized greedy algorithm, performs better than both of them. And on this category has a totality ratio of about 99%. So this is a little bit lower than 99, this is a little bit lower than 98%. But still they are much better than their approximation guarantees. Let me make a short detour regarding variable orderings and repetitions. So I've already mentioned the result by Costello, Shapiro, and Tetterly that says that if you take a random permutation, this improves the worst case guarantee. But this is not true, unfortunately, for the instance sets. So if I take Johnson's algorithm with a random permutation, the approximation ratio actually decreases by almost 1% for the STF category, and even more for the MSF category. The same picture for the randomized greedy algorithm. Question is, what's going on? So hypothesis would be that apparently industrial applications have some kind of, the ordering has a kind of a meaning. So apparently when these instances are encoded, there's some semantics here. And if I run the same algorithms for random ordering on a random instance, where I would not expect any symmetry, not expect any meaning, everything should be nicely symmetric, then in fact I don't see any change in approximation ratio. So I would guess the explanation are structural effects. Just x1 to xn. So the instance is encoded in a way where each variable has some index, and I just take that ordering. Yeah, but I think that's interesting that industrial applications apparently have some kind of structural properties, and the question is, can we exploit that somehow? The other thing is, I want to mention briefly, a randomized greedy algorithm makes a random decision each step. So of course I could ask, what happens if I run it multiple times, just return the best solution it has found. Unfortunately, the increase is very low. The increase is just 0.07%. And still, the randomized greedy does not achieve the performance of Johnson's algorithm. Okay, let me briefly describe local search. Here I want to point to a paper of Pankratov and Borody in 2010. Yeah?
Could you remind me what Johnson's algorithm was?
Oh, Johnson's algorithm is very similar to the algorithm we've seen before, to the two-pass algorithm. Basically, it looks at the variables in arbitrary ordering. For each variable, it looks at the clauses that appears in. And you can think of the basic computes which clauses would be newly satisfied by fixing it to 1, which clause would be newly satisfied by fixing it to 0. And then unit clauses are doubled in their weight in order to make sure that those have a special treatment. And this is a simple version of Johnson's algorithm. Okay, the first algorithm they considered is walksat. Walksat is a GSAT. This is a very famous random walk where you, in each iteration, you pick an unsatisfied clause, pick one literal according to some heuristic, and flip it. And by flipping it, you will satisfy this clause, but you might unsatisfy others. And this strategy has been improved over many, many years. Many heuristics are applied. It applies also kind of restarts. Yeah, it has a decent, we see it has a decent performance, but it's worse than the greedy algorithms. But still, it's fast. More interestingly is non-oblivious local search. Was proposed by Khanna, Motwani, Sudan, Vazirani. So we consider one flip. We start with some assignment. Then we consider one flip environment, meaning we look at each variable and compute how much progress we would make by flipping this variable. But we don't measure directly the progress in terms of satisfied clauses, but we have a potential function on top. That's why it's non-oblivious local search. Basically, I evaluated with starting from the all zeros assignment, starting from a random assignment, and starting from the solution obtained by the two-pass algorithm. And the last variant is the best. And it obtains a performance which is slightly better than a two-pass algorithm, but also comes at a higher computational cost. I would also like to mention that in Pankratov and Borodin's paper, they point out that non-oblivious local search is basically the best local search method if the number of flips is bounded. So it has, you can say, it gets to a good solution quicker than the other paradigms. The champion of the Pankratov and Borodin paper is combining non-oblivious local search with taboo search. Taboo search is a deterministic strategy. Once you have arrived at a local optimum, you start this taboo search, which is a deterministic way to walk out of this local optimum by making steps that decrease the value, walk hopefully far enough away, and then start again with non-oblivious local search. And in their paper, they show that this combination performs very well. In our evaluation, it does not. So the approximation, or the totality ratio is slightly above 90%, and it's very costly. The question is, what's going on? Looking closer, we see that this algorithm hardly ever terminates. If it terminates on time, so we have a time bound of 120 seconds, if it terminates on time, then the approximation ratio is comparable to the greedy algorithm, but in most cases it does not. I think the strategy is just too time consuming. Particularly benchmark instances have become much bigger. They evaluated it on benchmark instances from 2007. We have 2014. So this strategy does not scale well. The best algorithm overall is simulated annealing by Spears. It's a quadratic time algorithm. So we have n rounds for each, n is number of variables. We have n rounds. And in each round, we consider each variable once, compute how much progress would we make by flipping it. If the progress is positive, the increment is positive, we flip the variable. If the progress is not positive, we actually would go over to reverse assignment. In this case, we make the step with a certain probability. And we take a risk. And this probability of making a step that does not improve, this probability is decreased over time. So as the algorithm continues over and over and over, the algorithm becomes more goal-oriented in the last rounds. And we see in the evaluation, this is the best algorithm that we have. It's over all categories the champion, but it comes at a very high computational cost. Also, I want to point out the quadratic time algorithm hardly ever terminates. Most of the time, it just exceeds the time bound. But still, up to this point, it has already good found assignment. Okay, the question is, can we get the performance of Spear simulated annealing, which is excellent, at a lower computational cost? So can we get the best of both worlds? I'd like to propose the following combination. So we run the two-pass algorithm, which is fast. And afterwards, we combine it with the last 10 rounds of Spear simulated annealing. Why the last 10? Well, these are the rounds where Spear simulated annealing is the most focused towards the goal. So it takes little risks, but it takes risks. That's crucial. Also, a nice thing is that it uses the same data structure. So once you've implemented the two-pass algorithm, you can implement this combination at very little additional work. And of course, it's very fast, and asymptotically, it's linear time. So let me show how it performs. So here we have the simulated annealing. It gets about 99.77% on this category. And here's the new algorithm that gets 99.75. So it essentially matches the guarantee of the simulated annealing algorithm, but does so at the computational cost, which is comparable to a greedy algorithm. Also want to point out at this point that this algorithm performs well on all the other categories too. In particular, it does not lose more than, say, 0.5% with respect to the best algorithm for a certain category. So it's a good overall algorithm. Okay, let me summarize what I've showed to you. We started with a simple deterministic two-pass algorithm that gives a 3/4 approximation for max set. Along the same lines, we can also get 1/2 approximations for max die-cut and max not all equal set. I think this paradigm of making a second pass, where you make in the first pass, make some sketches about the input, and in the second pass, locally optimize these sketches, is a very interesting paradigm. And it would be interesting to see to what other problems we can apply these ideas, particularly other max CSPs. Also, it would be interesting to study the inherent limitations of these two-pass paradigms. And the natural approach would be to see if we can adapt one of the information theoretic models proposed by Borodin and his co-authors to study these limitations. But there's a problem, right? Because these information theoretic models, they rely on that the input is not revealed before the algorithm has made decisions. But here, a two-pass algorithm first considers the whole input we made before committing to any assignment. So the gist seems to be to somehow restrict the amount of information that the algorithm can remember from the first pass when making decisions in the second pass. In the second part of the talk, we've seen some experimental results on the benchmark set. We've seen that there's a new algorithm combining the two-pass algorithm and simulated annealing that offers a good performance at high speed, an excellent performance at high speed. But we've seen that greedy algorithms are much better than their respective worst-case guarantees. And I think that there's a huge gap. I mean, 99-point-something% in practice towards 2/3 or 75% in theory. That doesn't really match well particularly, it's quite disappointing that the better worst-case guarantee does not give a better performance in practice, and this seems independent of the category we look at. No, yeah, that's a far away goal. I mean, that's that. Yeah, but still, I would like. I mean, I think there's kind of a somehow the worst case shooting for a worst case guarantee does not give algorithms that perform really better. I think that's my point. And I wonder, is there a better way to describe what makes an instance hard? Is there a better way to describe the properties of these instances to come up with algorithms in turn that perform better on these instances? So somehow we do all this work, get better approximation guarantees, and then in the end we see the trivial thing was better than what we came up later. So I wonder if we can somehow mend this gap between these type of instances and the worst case analysis. Okay, thank you. In this case, it's in fact simple. Yeah, max cut is just a special case of max 2 set. So if you get a 3/4 approximation for max 2 set, this translates into 1/2 for max cut. Yeah. And conversely, there is nothing. Well, I mean, it's a special case. So if you get a better guarantee for max cut, this just means that you can solve that. Solve that type of max 2 set instances. I mean, you can compute the corresponding value, but it's just a subset. You're asking whether you can reduce it back, right? He's asking whether you can reduce any max 2 set instance to max cut, and that's not. I mean, probably you can do something, but I'm not sure what you would lose. So the containment is strict. So max cut is a strict subset of max 2 set.
Right, that's what you said. So
yeah, I would not know how you. Yeah, it's not clear whether you can really represent each constraint as a max cut curve. I mean, there's also generalization of max cut called max colored cut, where you have edges you want to cut, you have edges you want to not cut. So this gives you a bit more flexibility. I think, yeah, you can do something. You can rewrite the max 2 set instance as a max colored cut instance. But then you lose in terms of approximation ratio. But that you can do.
And are there relations between directed and scat or the other problems you mentioned? So there are not many relations like this between approximation guarantees between the different problems you mentioned.
So I think max not all equal sat somehow also generalizes max sat. So there's some connection there. Max die cut, I'm not aware of. I mean, of course, max die cut generalizes max cut, so probably you can, but I don't know what you gain from going from max cut to max die cut. Yeah, but think about the other point here. I think you can really, you can do that. You can represent a max sat instance as a max colored cut. You can basically look at the quadratic form of the max sat instance, max 2 set particular, and you can rewrite that as a max colored cut instance. So you can say it again?
I'm aware of at least 3 other 1/2 approximation algorithms for max die cut.
Yeah, I mean, you can use the original bookbinder algorithm that gives 1/2. You can Halperin and Zwick. That's with LP, yeah.
Yeah, and then there's the Halperin's with
right. I think they also have a kind of a best of many approach where they don't need to invoke flows or LPs. So they basically have, there's another paper by Halperin and Zwick where they compute different cuts. One random cut and one is like based on paths that they choose in the so that's also gives 1/2 approximation, I think.
Your algorithm is faster than theirs?
Yeah, I mean, I would say, it's a hard guess to make having Bill here. I would think.
No problem on 10 million variables.
But it uses combinatorial algorithm.
I think the two-pass algorithm is very, very fast. I mean, you've seen that.
I don't know algorithms with algorithm might have some fast interpretation. I'm not sure. I thought it was combinatorial too. Like they're showing themselves with Maxwell computation combinatorial.
So I mean, the algorithm that I had in mind is taking a random cut, and the other one is basically take disjoint short pairs. And this probably can be done very quickly too. Which one is faster? I guess you have to try. And with respect to the LP, I don't know how fast you can solve an LP with, say, 10 million variables and 50 million edges. I don't know how fast that would be. Do you have any?
70 longer than a second. I said max flow is pretty easy. Solve it. Solve it in a second.
I'm not sure that they actually use it. So it's some faster way. I have to check.
Anupan, what's the question?
So the sort of the fact that the random permutation algorithm was doing worse than the rest of them seemed to suggest naively that there was some, as you mentioned, there was some structure in the instance. And did you sort of happen to play around with the instances to see whether they were somehow decomposable and there was locality of variables, and whether that was really helping? Or is there some insight into what made them?
That's a very good question. Exactly. I don't know. I know when it's known for SAT instance that they have these backdoor variables. So if you basically choose those right, the rest becomes easy. And there is some structured information about that. I don't know. So actually what I'm doing currently is like I have all this data. I try to evaluate with some machine learning methods to see if there's some pattern, so if there's something more to be concluded, what makes an instance easy, or conversely, can I make a prediction if an instance is easy for a complete solver if I know how the greedy algorithm performs on it, or something like that. But it's really weird. So I mean, these complete solvers, for some industrial instances, they solve 10 million variables in less than 2 minutes. And then they fail on other instances from the same benchmark set that just have 300 variables. And you can run the complete solver for 3 weeks and it does not get anywhere useful. So it's absolutely not clear. And I have contacted the authors and they said, well, we have no understanding what makes the instance easy or not. There's a lot of work to be done there.
Just viewing this as a hypergraph and seeing how decomposable it is, whether it's got sparse cards, whether just maybe enumerating over a few variables and seeing if there are any.
Yeah, good point.
Did you notice any difference between two-pass estimated annealing versus Johnson's algorithm estimated annealing?
I haven't tried it. But I would also mention that only doing simulated annealing on its own, short 10 rounds, is already pretty good. So it's not as good as two-pass plus simulated annealing, but it already makes a huge step towards the simulated annealing itself. So just doing the last 10 rounds of...
You must start with some order, right? You start with some solutions with simulated annealing.
I can just start from the all zero or random without using the two-pass to find a good starting point. And then already it converges within 10 rounds to something which is pretty good.
I think you answered my question, but I was going to ask, did you just try random and then simulated annealing?
Pardon?
So you did try random and then simulated annealing for 10 rounds?
Sorry, say again.
So did you try random followed by simulated annealing?
Oh, you mean a random starting assignment? Yeah. So that's, I said 10 rounds of simulated annealing with random assignment is already pretty good.
What's the improvement that you get from two-pass plus simulated annealing?
So I think these are all pretty close to each other. So basically benefiting from something like it's basically 0.2% or something. So, I mean, 2 pairs already is very close. Two pairs on its own gets something like 99.5. And then simulate annealing, the full version, gives 99.77. So already the gap is very small. So to make this last increase of what is 0.27%, that's basically where what we need the 10 rounds for. So we are almost there with the 2 pairs already, but then in order to close the gap, we use the last. Yeah, I mean, it's also, I mean, basically, what we expect is that the running times increase by a factor of 6, and because you have basically 12 rounds towards compared to 2 rounds. But in fact, it's slightly better. The additional cost is a factor of 4 or something. But still, the question is it really worth to put all the effort into that just to get a last 0.5% or something, or 0.25% in terms of fraction? I think this depends on the application at hand. So I was told that improving a little bit, just getting a few more clauses out of it might be worth a considerable amount of money. So then you want to basically be as good as you can be. But I mean, it's a trade-off. Also, you can basically trade off the rounds you do. Here I said 10 rounds, but you can also do 15 or 20 of just 5 and see what you get.